Okay, so last time we finished with classical mechanics very quickly, but that's a brief outline of classical mechanics. So now let's move to quantum mechanics. Now there are only three of us, so I'm just thinking that who never took a class on quantum mechanics? Okay, so then let's do it.
I'm sorry.
No, that's perfect. So quantum
I mean, if you
mechanics.
want to skip it, you could, and I'll go do some.
No. I was actually afraid that everyone will say yes, we know quantum mechanics. Then I wouldn't know what to do because I prepared an introduction to quantum mechanics.
Okay, thanks.
Okay. So let me make a list. So I'm not going to discuss physics. I will discuss the mathematical framework. So in classical mechanics, so what do we have? We have observables. These are C infinity M with coefficients in real numbers. So it's Poisson algebra. And what is the quantum counterpart of this thing? So, so first, the algebra of observables. It's an associative algebra. Over complex numbers with the, let's call it A, with a C antilinear involution. So this means that AB star is B star A star, and lambda A star is lambda bar A star, where lambda is a complex number. So in this complex vector space with this with an associative algebra structure with this C antilinear involution, we have a real subspace. These are elements that are self-adjoint. A star is equal to A. I mean, obviously, it's a real vector subspace, and this is the AR is the space of observables. Obviously, this is just a subspace, not a subalgebra. Because if you have two Hermitian operators, if you take the product, say it will be B star A star, and it will be BA. It's not equal to AB. So, okay. So we have the space of observables, that's a real vector space, and the algebra of observables. And these are two different things. One is the subspace in the other. It's like you have, say, the space of complex n by n matrices with Hermitian conjugation, with this operation. In this space, you have the subspace of Hermitian matrices. So the Hermitian matrices, they just form the vector subspace, not a subalgebra. Okay, and this is the counterpart of what we have here. So now, so now here we also have classical states. Classical states are simply linear functions on C infinity n, but these are probabilistic states, so they have a normalization L of 1 equals 1, and let me put it this way: they are given in the classical setting. They are given by so LF. It's an integral over M. The density of the state, where this is a density, and it's a probabilistic measure in the sense that L of 1 is the integral M rho x 1. It means that the probability M is 1 of this subspace, and then L of U, sorry, maybe I shouldn't say, yeah, L of 1, yes, and then the probability of U is just the integral over U rho x. So you can say that it's a probabilistic linear functional, or you can say that you have the probability measure on the phase space. Probability measure on F. So what do we have here? Here we have quantum states. So these are just linear functionals. Which are real. Rho A belongs to R if A is equal to A star. Then row of positive element, and these are positive elements. It's like if A is a complex matrix, then A times A Hermitian conjugate will have only positive eigenvalues. This is positive, and row A star is 0 if and only if A is 0. And normalized row of 1 is 1. And this is really the counterpart of the classical states. So mathematically, quantization is really a passing from Poisson algebra to an associative algebra. And we will discuss it kind of exactly how it happens in a moment. And states are just this quantum states. Okay, so let's look at examples. Okay, so first, sort of typical example, in a sense. Suppose that we have a vector space.
Sorry, just to check something. So the quantum analogy for observables, is that really, should we be thinking of it as AR or AC or the whole structure?
These are these are very special linear functionals on AC.
So no, I don't mean the states. I mean the observables.
The observables.
Yeah.
You mean quantum observables?
Yeah, the quantum observables. Should we be thinking of it as AC or AR? Oh, okay. You actually
That's,
wrote that. Okay. Yeah,
yes,
sorry.
yes, yes.
My mistake.
These are the
Okay.
observables.
So what role does the AC serve?
Just whatever operators, roughly speaking, say whatever operators you have, they will be in AC.
Okay. Okay.
So
But there's no standard process to start from AR and complexify somehow.
it's
We really want
it's
to.
well, as a vector space. I think there is a process like this, that AC is the complexification of AR. You know, let me check this, and I'll tell you exactly next time.
Okay. Okay. Thanks.
I think it's next time that we will talk about deformation theory, or maybe so towards the end today. So I think that's correct. You know, every complex matrix, n by n matrix, is the complexification of Hermitian matrices.
Mm-hmm.
So in this sense, quantum observables should be the complexification of the Hermitian matrix.
Okay.
Why complexification? We will see this. It's roughly speaking because the operator DDX is not Hermitian; it's anti-Hermitian with respect to the usual L2 product. It's I DDX that's Hermitian. So in order to have this standard, so that's roughly speaking why.
Okay. All right, thanks.
Okay, so a typical example. So let's suppose that we have a vector space where we have a representation of our algebra A. So assume that V is a Hermitian vector space. Let's denote it this way. So it means that X, Y, this is equal to Y, X. And then I assume that P is Hermitian or star representation. What does it mean? It means that if you will take this, it's the same as Hermitian conjugate of the operator P, and Hermitian P means that this is equal to P of PV of A star. In other words, representation respects this anti-linear involution. Okay, So in this case, states are the following. Suppose we have a Hermitian operator rho with non-zero eigenvalues. Normalized in the sense that trace rho is 1. In other words, sum of eigenvalues is 1. If V is finite dimensional, then it's just sum of eigenvalues. If V is infinite dimensional, well, we have to be careful about the conversions. In this case, we assume that rho is trace class, meaning that trace rho exists, and it should be 1. So, so in this case, corresponding state, let's call it L rho A, is just trace of rho A. And rho is called the density matrix. And there are two important examples. V is finite dimensional. This is what people in quantum computing do. Quantum computing, quantum information, typically they have finite dimensional vector spaces. And the other example is, say, when it's L2Rn, so that's the Hilbert space with this norm topology, and we require that the trace is the usual trace in this Hilbert space. We require it to be trace class, and it's an invariant notion in the sense that you choose a countable basis in the Hilbert space, then trace is just the usual matrix trace, and then you can prove that with respect to bounded operators in the Hilbert space, this trace doesn't depend on the basis. Okay, so more sophisticated examples is when you have L2 on some manifold, but if it's just a manifold, then you have to fix some measure on the manifold. For example, Riemannian volume typically, and so on. And then the kind of a little bit more exotic example of spaces that occur in quantum mechanics, this so-called half densities. And they work in case when you just have a manifold, no extra structure, no volume form, no measure. So half densities. Half densities is the following. Suppose that you have a manifold Q. It has some cover, some atlas of coordinate neighborhoods, and for each M alpha, we have coordinate functions Rn. It's not isomorphic, but it's mapped to Rn. It's an isomorphism with some open disk in Rn. So this gives local coordinates Q alpha I. And then in local coordinates, you have the usual density. It's the volumes of elementary parallelepipeds over which you can define the Riemannian integral locally. So first, let me define a